Stringing a tennis racket is a surprisingly precise process. The drop weight stringer is a critical instrument used worldwide to restring rackets. This is the most accurate and simple way to restring a racket. So how does tension actually affect tennis? Tension is a trade-off between power and control. You can imagine a tennis ball being hit by a tennis racket like someone bouncing on a trampoline. A lower tension, under 50 pounds, creates a more pronounced trampoline effect, where the strings deform and snap back, propelling the ball fast. A firm tension, over 50 pounds, gives you a more firm string bed, which allows the player to have more control of the ball. At higher levels of tennis, tension is extremely important as you can feel a difference between 1 pound of tension. Here's the setup with the string and tension in the racket set up. The weight is slid until you get to the tension that you want. The string is wrapped around the first clamp, and then the weight is dropped to a horizontal position to get the desired tension. Next, I set up a simplified free body diagram of the stringing machine. At a high level, moment must be equal in the system. So string tension times distance 1 pinned to string must equal weight of the slidable weight times distance 2 plus the weight of the rod times the distance from the pin to the center of mass of the weight of the rod. Then solving for string tension, we can get our equation. Now that we have our string tension, what I want to explore next is if we disregard metrology, is it possible for a bad string tension output? I'll explore a theoretical scenario with 3 errors to see how that affects our string tension. The first theoretical error comes from a thermal error. Let's assume the scale was calibrated right after the rod was extruded at 350 C. Now that it's being used in a normal room at 15 C, the scale has contracted. Next error comes from a cosine error. Let's assume in this scenario that the user does not understand the impact of cosine angular error, so the lever arm is not dropped to 90 degrees, but instead 75 degrees. The last error comes from an encoder calibration error on a lathe. Each step is supposed to move 1 millimeter, but this encoder was calibrated to move 1.1 millimeter each step. This causes the lathe to cut more material than what is wanted, causing the weight to be less mass than nominal. Calculating the nominal tension without any error, we get 46.5 pounds. Calculating the tension with the thermal, encoder, and cosine error, we get 37 pounds, creating a difference in tension of 9.3. We can verify our calculations by applying the error values on our actual stringer. So first, I strung the racket with the nominal values, 3.4 kilogram weight and 0.241 distance from the center. Next, I used the values with the errors, which equals 2.7 kilogram weight and 0.231 meters distance from the center. After stringing each racket, I measured with the Turner string meter. The nominal racket had a tension of 45 pounds, and the error racket had a tension of 34, resulting in a difference of 11 pounds. In summary, metrology is extremely important regarding racket stringing. The calculation yielded 9.3 pound difference, and the physical trial yielded 11-pound difference. Since pros can feel a difference of 1 pound, the tension difference from these errors would make this racket unplayable.